Okay, so thank you for the introduction. So this talk is going to be about AutoLock, and it has been a joint effort between Mark, Gorka, and Thomas from Worcester Polytechnic Institute, as well as Leandro, Johan, and me from Fraunhofer AISEC. So let's take a look at the big picture first. So we saw that in the past 1 or 2 years, cache attacks transitioned from x86 processors to mostly ARM-based processors, and we know that these attacks are possible on that new processes. And since cache attacks are a practical threat, of course we want to get a feeling of how vulnerable our systems are and what risk they face from cache attacks. But this isn't always so easy because we don't know everything that's going on into or in commercial microarchitectures, right? So this is where also AutoLock comes into play. So AutoLock is a undocumented performance feature of inclusive cache levels on ARM that actually has a security implication, and that is it makes eviction-based attacks harder than what we previously thought. But then again, it is not an ultimate countermeasure, so we still need those to defend against cache attacks. So that's the big picture. So let's maybe look into a bit of a cache basics that we need to understand what AutoLock is doing. So let's consider this kind of system, which is very common on ARM processors. So we have a multi-core system. We have two levels of cache. Cores have core private caches separated into instruction and data side, as well as there is a unified shared last level cache. All of them are set associative, so there are a number of sets and a number of lines in those sets. Of course, there's also some external memory and a couple of programs that are running concurrently on them. So if you start a program, it basically brings instructions and data into the cache hierarchy. And there's one important property that tells how these cache levels interact with each other, which is called the inclusiveness property. So inclusiveness tells us everything that is in higher cache levels has to be in lower cache levels as well. And what we see on ARM is that typically one of those sides, so either instruction or data, is inclusive. In contrast to x86, for instance, Intel processors were fully inclusive usually. So let's assume we have a data-inclusive side. That means we have to store this data also in a level 2 cache. And this holds for all the data that we're going to load. And of course, caches are just of limited size, so eventually we're going to run into something that's called eviction, so we have to replace data. So on the level 1 part, that is not a problem with inclusiveness, so we do not violate it because the level 2 cache can just contain more data than the level 1. The situation changes a bit if, let's say, B starts to run, load some instructions, load some data, and happens to load everything in the same level 2 cache set. So that's possible. And at some point, it's going to override some of A's data. But that now violates the inclusiveness property. So what the cache controllers have to do is they have to talk to each other and say, okay, well, I evicted a cache line, so please, level 1 caches act accordingly. And in this case, we have to remove B from the level 1 cache to not violate inclusiveness. So that is a very interesting property for 2 reasons. So first of all, that's a rather costly operation, of course. If I evict lines from the level 2 cache, I have to do all of the broadcasting. And second of all, that is very interesting for attacks, because now all of a sudden, B has some impact on the core private caches of A. So let's look into cache attacks, and what they're usually trying to achieve is what we previously saw on that conference as well, if you think of Prime and Pro, for instance. So we want to remove all of A's data from the cache, and on an inclusive cache, we can do that by just filling a level 2 cache set with our own data. So let's assume B is malicious and wants to fill the cache set. So what it is doing is actually just loading in some more data into the cache set until it removes all of A's data. Yeah? So, and we see that if we look at C, then if B overrides that in the level 2 cache, of course, inclusiveness ensures that is also removed from the core private cache. So we end up with a situation where we actually have removed everything of A's data from the cache. And then the attacks continue, right? So this is what usually eviction-based attacks do. And in the most practical sense, cross-core eviction. So we only target the last level cache. Yeah, so in the step after that, so once B has evicted the entire set, then A is basically reloading the data. That might depend on some secret, and this is what we want to learn, right? So if you do this little experiment on an actual system, this is how it might look like. So we can see here if B is actually doing that eviction, and if A is reloading it, so this is what we see here, that's the reload times of A. Then in the red color, we see that all the reloads after this cross-core eviction has happened, they actually come from RAM, so they are slow. Whereas if B just does not do this eviction, we see that the accesses all of a sudden just happen all from cache and are fast. This is what we want to have in an attack. We want to have this this possibility to distinguish and to have this cross-core eviction. So in literature, eviction-based attacks make one side of the spectrum. The other side of the spectrum are flush-based attacks, relying on flush instructions to specifically remove data and instructions from the cache. So let's compare them on ARM real quick. So on ARM, the situation is that flush is still, it's easy, it's fast, it's robust to use. But the case is if these flush instructions, in contrast to x86, have only been introduced in the very recent version 8 architecture version, and they have to be enabled for usage in user space. So that means that flush-based attacks only affect a limited number of devices on ARM. Whereas eviction, which is, of course, more complex, slower, and more error-prone, as we saw, applies to all architecture versions and can be done from user space. So we have a larger number of devices that are affected by them. And this is exactly where AutoLock comes into play. So we have cross-core eviction-based attacks. We have the same setup as before, but now we have a cache that implements AutoLock. And what AutoLock means in a very simple form is that we have an extra bit per cache line that tells us which of those lines are contained in higher cache levels. So we can see here that both A and B's data, they have at some lines a 1 bit, but for instance, the lowercase a has a 0 bit, so it's not contained anywhere. And this bit is what is usually called like an inclusion or indicator bit. So and then let's make B again try the cross-core eviction. So B is loading some data, placing it into level 1 cache, and of course we have to update the level 2 cache as well. So what we do is we first reset all the bits that have now cleared because they're not contained in the higher cache levels anymore. So we clear that. After that, we have to place U, of course. So what we look at is all the lines that have a 0 inclusion bit. And this is where AutoLock interacts with line replacement. So line replacement just tells me which line I should select for eviction. And in a cache that implements AutoLock, we're just going to select the lines that have a 0 bit. So we look at the lines that are available, we place U, we update the inclusion bits. And this is what we do some more to fill the cache set. So we load some data, we look at the lines that are available, and we update the bits. We load data, place it, update bits. And eventually, of course, we're going to overwrite some of A's data, for instance, lowercase a, which is not a problem because it has a 0 bit. So we can just override it and everything's good. We load some more data, place it. But then, of course, we actually want to replace the last line of A. And that is not possible because this is still contained in the higher cache levels. So that's like an implicit lockdown happening. And this means that we cannot do this cross-core eviction anymore. So we fundamentally interfere with these attacks because essentially B cannot learn anything anymore about what A is doing with its data in the cache. So that's the fundamental effect of AutoLock on cross-core eviction attacks. So a more formal definition maybe, so AutoLock, what it is a patented and undocumented performance feature of inclusive cache levels. So the only public node that we found is a patent held by ARM Limited, and other than that, it's not documented in any architecture or technical reference manuals. It is a performance feature because, as we recall, we are preventing these eviction broadcasts to the level 1 caches, which makes the runtime faster. And how does AutoLock do it? So AutoLock is a transparent feature. So there's no interface to it. We cannot configure it. We cannot see if it's enabled or disabled. So it is a lockdown, but it is not a traditional lockdown. So a traditional lockdown or programmable lockdown is something that I can configure and register and just lock cache lines or cache ways. But this is done automatically and conditionally. So these lines are only locked if they're contained in a higher cache level. And for these reasons, we dubbed this feature automatic lockdown, or in short, AutoLock. So what are the implications of AutoLock now? So if you take a look at the attacks again, then we see AutoLock fundamentally interferes with cross-core eviction-based attacks. Whereas on the same core, that is not a problem, because if A and B run on the same core, B can still clear the entire level 1 cache and thereby unlock all the lines in the level 2 cache. So same core attacks still work. And also, flush-based attacks work. So that's just a different way of evicting data from the cache hierarchy. So that is the impact in theory, and how we actually recognize it in practice is something like this. So we recall the reload times of A from earlier, which were on the Qualcomm Crate 450. That's an ARM-compliant processor core. And we saw that there's a clear difference. But now we repeated the same experiment, the same code on an ARM Cortex A57, and all of a sudden, regardless if we do eviction or not, the reload times are always from the cache hierarchy. So this is how we encountered it, and this is what we use actually, this cross-core eviction-based method to test chips if they have AutoLock or not, because it's not documented. So we have to have some way of testing chips if they feature it. And this is what we did. So we found AutoLock in a number of ARM chips, so 2 version 7 chips, 2 version 8 chips, in different contained in different system on chips from different manufacturers, and we also see that the ARM compliant core from Qualcomm does not have this this behavior, this AutoLock. So what this means, if we extrapolate these results a little bit to, let's say, for instance, the smartphone market, that we can see that from the manufacturers that cover like the vast majority of system on chips employed in modern smartphones, we see that quite a lot of them feature ARM designs, obviously, but there is still a lot of diversity in the market. Yeah? So this ARM licensing ecosystem causes like a large diversity in the system on chip market, unlike x86 processors, where we have maybe like one way of Intel to do it and one way of AMD to do it. So the question is, like, if presumably a lot of chips have AutoLock, why did no one before recognize it? And that is a list of previous work that tried user space cache attacks on ARM processors, and we think that there's like a couple of reasons why they didn't see it. So first of all, device selection is very important. So the Armageddon paper, for instance, on last year's USENIX, they used they had one test device which was a Qualcomm Crate 400, which we think simply doesn't feature AutoLock. Or there's yet another device where they just were able to use the flush instruction. So attack selection is another important part. So if you focus on flush and reload attacks, then you will not run into AutoLock because you're not doing cross-core eviction. And lastly, also your device properties can play a role. So if you happen to be on a single core system, then as we know, same core attacks work. So even though you're doing eviction, you will not run into AutoLock or any of its effects. So now that we know AutoLock exists, it has an adverse impact on attacks, and it's found on a couple of system on chips. The question is it a countermeasure? Does it help us to actually defend against cache attacks? And the answer to that is it's not ultimately a countermeasure. So first of all, let's recall that we have still a number of chips that either do not feature AutoLock, for instance, the ARM-compliant cores that we tested, or where you can just simply use user space flush instructions to do attacks. Second of all, same core attacks are still possible too. Let's just think of an ARM trust zone application in a compromised operating system. Then you can still schedule attacker and victim on the same core and do an eviction-based attacks regardless of AutoLock. Then there is something that we call like remote evictions. So recall that the level 1 caches, they have a rather small associativity. So a little bit of unrelated activity, a little bit of background noise will help in evicting lines that are in the level 1 and thereby unlocking them in the level 2. So even though I don't do anything, this happens automatically. So either the program that I want to attack does it by itself, so it's doing a self-eviction of its own data, or I can just, for instance, try to increase the load of my operating system and thereby cause these remote evictions on my target core. And this is especially interesting if we take a look at, or if we consider that we might not, if we want, or if an attack happens where we want to attack someone, that we can maybe target more than just one cache line. If we are fixed to one cache line, we very likely will have problems observing it on a cache that implements AutoLock. But if you think of AES-T tables, for instance, that are stored on a large number of cache lines, then it might be sufficient, or it might be possible to just observe more than just one line and still learn something from our target. And to demonstrate this, we implemented a cross-core attack. So it's a wait-a-minute attack by Yarothoki et al. It is originally a flush and reload attack, but we implemented it as an evict and reload attack. So we're doing cross-core eviction. And what the attack is doing, it's basically observing the usage of the cache lines where the T tables of AES, the lookup tables, are stored on. So they are basically evicting a line, doing an encryption, and then checking whether the line has been used. And from that, you can infer the key that has been used. So the original attack only observes one line per table. So what we did is we just built a very simple redundant version of it by observing all the lines, doing the attack with the observation on all the lines, and for all the keys that we get out, we do a simple majority vote on the key bytes that come out. So this is our very simple redundant version of it. And we implemented it on a test environment featuring an ARM Cortex-A15 that implements AutoLock, and also some operating system, of course, because we want to have this background activity, right? So these are the results. So what you can see here on the y-axis, the number of key bytes that we recovered, and on the x-axis, the number of encryptions that we used to do so. And we can see the first line that is drawn here is the original attack in the same core scenario. So there we don't have any effect of AutoLock. And we see that with very few encryptions, we recover the entire key. The situation changes if we move from a same core to a cross-core attack scenario. So in this case, we directly see the impact of AutoLock. So even though we invest like a large number of encryptions, we are not able to get the entire key. And the fact that we even see something is exactly this effect of remote eviction. So one of those lines we were observing in the original attack might just have not been affected by AutoLock. So we are in the cross-core scenario, and this way we cannot do an attack. But if we employ our redundant version of the cross-core attack, then we are again able to retrieve the entire key with similar efficiency than the same core attack. So this should just demonstrate that under certain circumstances, we're still able to launch cross-core eviction attacks even on systems with AutoLock. And that's just to emphasize one more time that it is not a perfect or ultimate countermeasure against attacks. So this already brings me to the conclusion. AutoLock is an undocumented performance feature of inclusive cache levels on ARM. What it does is it inhibits cross-core eviction-based attacks and has an adverse effect on them. It is predominantly implemented on Cortex-A designs by ARM based on our results. And even though it has these adverse effects and it's implemented on a number of devices, it's still not a countermeasure, and we still need good countermeasures against cache attacks to protect our systems. So thank you for your attention, and I'm happy to answer any questions.
Thank you, Andreas. Any questions? Okay.
Hi, Stefan Suri from MSR. Very nice finding this AutoLock thing. I didn't know about. Like, this is great, and I enjoy your talk. I just wanted to have you. Can you also comment a little bit on? Are there any drawbacks on using AutoLock in a cache with respect to performance? Have you measured that? In other words, it's probably hard to measure because you need a comparison. You need the same architecture with AutoLock and the same architecture without AutoLock.
Yeah. So you mean like the fact that AutoLock is implemented in a cache? Like what kind of performance hit are you getting?
Can you comment on? I mean, I'm just curious.
Like I can give you my intuition.
Sure.
So I mean, AutoLock is a performance feature, and it prevents these eviction broadcasts, right?
Yeah.
So in a sense, it should give us some performance improvement.
Correct.
And the only downside is, like if our last level cache is getting smaller and smaller, we're going to like lock lines and take them away from other processes, because that can happen, right? But what we saw is that the last level caches in the typical case are just big enough that always lines will be available for eviction.
I see. So, and the other thing, do you have any comments as to why you think AutoLock is not enabled in all these other SoCs made by Qualcomm? And do you think they just do any?
That is something that you may expect from the feature being patented by ARM. So we assume that other companies or ARM compliant cores are just not using it, because they would have to pay some kind of royalty fees to ARM to use it.
So you think it's a cost issue?
We think so,
yeah. Okay. Very nice work. Thank you.
Hi. I'm Sinisha from ETH Zurich. So I read the paper and I listened to the presentation, so I have just one comment. So in the paper you wrote that these tests that you've done on the ARM processor were done on bare metal to avoid interference from the OS and so forth.
Yeah.
So my question is regarding that. I mean, that doesn't seem to be like a real-world situation. So if you would really be doing in a cache attack, you wouldn't be doing it on a bare metal, you would be doing it on a normal operating system, because the attacker wants to compromise a running system, not a bare metal implementation.
Yes.
So how would you comment a little bit about that? Because that doesn't seem like a clear result.
Yes. So thank you for the question. So basically, like when we talk about testing for AutoLock, what we actually like had in mind is either some engineer that wants to find out whether its system has this feature or not, or if you think of an attacker, then the advantage that an attacker has that he has to determine AutoLock only once on every SOC. So it is also realistic that an attacker just buys a couple of devices, tests them for AutoLock in a bare metal scenario, and then just knows once I am on another system, like whether there's AutoLock or not. So that was more like the intention that we had with those tests.
Okay, thanks. So another comment is that I like the work and this AutoLock and everything regarding that, but that makes me question all the other ARM-based cache attacks papers that are out there. So if people didn't really see this feature or experience this feature, then everything falls down into the water. All of these ARM-based cache attacks. How would you comment on that?
So I think that, like, for the reasons I gave earlier, there's still a lot of valid situations where you won't be affected by AutoLock or where you won't see AutoLock. So, like, I think of AutoLock as being like another challenge in one of the attack vectors that you have, like an additional challenge in there. But it is not like it doesn't affect flush attacks, for instance. So it is just like one more obstacle that you have to overcome.
Okay. And the last one, if I may for a minute, I saw it on the slide, it says same core attack on trust zone.
Yeah.
How would that actually work? Because in trust zone, it changes completely to the secure world, so you can't really pouch anything or touch anything in the cache, because while it's running in the secure world, you don't have any access.
You mean, like, can you rephrase that maybe?
Yeah, so if I'm running an application in the secure world,
Yeah.
there's no way for you from the normal world to access the cache.
Yeah.
So how would you perform an attack?
Well, in the ARM cache levels, secure and non-secure world can still evict each other's cache lines. So these attacks have been shown before.
I don't know. That's why I'm asking.
Yeah. Okay.
I don't know. That's why I'm asking.
So that was, for instance, the True Spy paper.
I just want to comment actually about this trust zone issue.
Mm-hmm.
So if you read the ARM trust zone spec, it says very clearly that the moment you change between normal world and secure world, you should flush the caches. So those are just pre-implementations of those attacks. And in general, in my experience, the industry who uses trust zone is very careful to flush the caches every time they switch back and forth.
Yeah.
Okay. Thank you, Andreas. Great work, and thanks for all the questions. Let's give him another round of